Welcome. In this video, I'll show you how to solve problem 6.19 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. This problem is the same as problem 6.21 from the second edition of the book. This question states as follows. It says, consider the 8n=2 states, and we will label the states using a ket, which is going to be 2LJ MJ. All right, it doesn't really matter how you label them, but it doesn't really make sense to put anything into the ket that we don't explicitly need or that doesn't really help us understand the configuration. So that is why we're going to be using this notation, of course. In the end, brass and kets, they are used to, reference a certain state. So if there's any other convention that is better for you, then by all means, go for it. It doesn't really make any difference. Well, we want to find the energy of each one of these 8 states under weak field Zeeman splitting. And we will then construct a diagram to show how the energies evolve as the magnetic field increases. We will have to label each line clearly and indicate its slope. All right, so that is the task ahead. We have to find the new energies under weak field Zeeman splitting. Now, let's remember, what are the energy levels under weak field Zeeman splitting? Well, the energy levels under Zeeman, maybe let's put a Z up here. This is the Bohr magneton times the landé factor G. Then we have mj, the quantum number, and we finally have the magnitude of the external field. So this is the formula that we found in the previous video. So if you don't know where this came from, then you will have to go back. And it's super important. This formula is exclusively for weak field Zeeman splitting, okay? We haven't gotten to the rest, to their parts yet, but the formulas will be different. So please keep that in mind. All right, so to find each one of these, we clearly need to know each L and J for GJ, and we also need to find, of course, or we need to know MJ. So that's why we labeled each state like this with L, J, and MJ, because those are all the values that we need. So we need to find the quantum numbers for each one of the states. Now, the way to do that is to use addition of angular momentum, right? So we have L equals, well, it can be 0 and it can be 1, so 0, 1, and S equals 1/2. So this means that we will have values of J, which will be 1/2 and 3/2 in the different combinations. So using this, we find all of the 8 states. We have done problems previously. I think we did not this particular example, but others. You can either do it manually or use the Clebsch-Gordon coefficients. Just look them up in a table. Whatever you want. This problem is really concerned about the addition of angular momentum part. We have already done that in the previous course. If there are questions, I'll be happy to add more videos on that topic. Let me know in the comment section. But as I mentioned, for now, what really interests us is to just go for the states. So I'm just going to take the states. These are the 8 combinations, right? I just use this up here to remember what each column stands for. So N, L, J, and MJ. And we now want to use this to find each of the elements from our energy levels. So actually need to move this a little bit. Okay. So we need to find JG, right? Because MJ is super easy. It's just plugging in the value. It's either 1/2 or -1/2. Well, it depends actually on these values. So it can be 3/2 and -3/2 as well. But it's a matter of plugging in, so it isn't too difficult. JG can be, or GJ can be a little bit more confusing, the G factor. So let's find that. Now, remember the formula for the G, damn it, for the G factor, we found in the previous video as well. And this was 1 plus J plus 1 minus L plus 1 plus 3/4. And all of this divided by 2J plus 1. Okay, so this is what we found in the previous video. So now we just have to plug our values in here. There are 8 states, but it will be very annoying to have to do this 8 times. So let's now look at this and see which states have the same quantum numbers. or at least the same relevant quantum numbers, because mj doesn't appear in here. So for example, states 1 and 2, right? It doesn't matter which ones you call 1, 2, which ones you call 3, 4, it doesn't matter. It's just an arbitrary number, a name, sorry. So these two states have the same values for L and J, while the next two states, these ones, also have the same values. And these other 4 states also have the same values. So we have 3 different values for JG. So we don't really need to do this 8 times. 3 is enough. So it is good to notice this beforehand. Otherwise, you will calculate this 5 more times than you have to. All right, so JG. GJ, damn it, the G landé factor, all right? For the case J equal 1/2, so 1/2, and L equals 0. So in this case, we have 1 plus, then we have 1 plus 1/2, so we get 3/2 times 1/2, so we get 3/4. Then we have minus 0 times 1, so 0, and then plus 3/4 again, so 3/4, and this is divided by 2 times j plus 1, but this is 3/4 as well. And so this up here is simply 2 times 3/4, so we have 2 times 3/4 here and here, so this cancel out and we have 1 plus 1. So this is simply 1 plus 1. So G for the case J equal 1/2, L equals 0 is 2. All right, next case, I'm gonna get rid of this and just leave the final result. So this is equal to 2. Let's use a different color. So now we have G, the G factor for J equal 1/2 still, but now L is going to be equal to 1. So this time we have 1 plus, and this is still 3/4. Then we have minus 1 times 1 plus 1, so minus 2, plus 3/4 divided by 2 times 3/4. So we can add these two together. So we get 6/4, and 2 is simply minus 8/4. So we can now add these and we get minus 2/4, which is minus 1/2, but we can leave it like this for now. And well, the 4s will cancel out and we are left with, let's see, 1, and then we have minus 2/6, which is 1/3. So this is 1/3. So this is 1 minus 1/3. This is 2/3. All right, so that is that value for G. So 2/3. All right, so we have one more, which is from these 4. So this is a case where J is 3/2 and L is 1. Whoops. And L is 1. So in this case, we have, once again, 1 plus, and now J plus 1 is 3/2 plus 1, which is 5/2. So that is 3/2 times 5/2 minus 2 plus 3/4 divided by 2 times this same thing, which is 15/4. So let's actually rewrite this part as well as 15/4. Right, and we can now, once again, add these two together, write this as minus 8/4. So this would be 18/4, and this right here is minus 8/4. So when we add them together, we get 10/4, which is 5/2. And down here, we can simplify. This 2 cancels out part of this, and we are left with 15/2. So this is going to be 1 plus the 2's will cancel out. So we get 5/15, which is 1/3. So we get 4/3. All right, so those are our 3 values for G, for the G factor. what was our formula again? Our formula was the Bohr magneton, which is a constant, times this G factor times M. So we are actually now in a position to find each one of the energy levels. So let me maybe duplicate this. How do I do that? Never mind, I'm just gonna do it like this. I'm just gonna copy this and go to a new page and paste it. All right, so let's now find each one of the energy levels for these. So for the first state, this one, now the energy, so maybe let's call it E1 because of the Zeeman effect. Now this is going to be the Bohr magneton times the G factor, which in this case is 2, times mj, which is 1/2. Maybe let me write this up here so I make sure that you are all following. So mb times jg times mj times b external. So this times b external. So this is simply the Bohr magneton times the magnetic field. I'm going to write the magnetic field as B because I'm lazy. I mean, there's no need to write the B ext for now. Next one, so the second one, this is the same except it has a minus sign because it's minus 1/2. So we get minus mu B times the magnetic field. All right, number 3, this one right here. This time we have a different value for the landé factor. So we get that this third energy level is mu B times, and what was our landé factor? It was 2/3. So now we have 2/3 times 1/2, which is mj, times B. So here we get 1/3 mu B times the magnetic field B, right? Because this cancels out. Yes. Next one is this. So here E4, because of the Zeeman effect, is mu B. And then we have 2/3, and this time it's minus. So it's basically the same, but with a minus sign in front. So we get minus 1/3 mu B times the magnetic field. All right, next one. I'm going to change colors. So now we have E5 because of the Zeeman effect. What do we have now? So this is going to be Bohr magneton times J, damn it, G factor for 3/2 and 1. So that is 4/3. I think I thought wait, what? Oh, never mind. Okay, let's continue. I thought it was, no, don't worry. All right, so our G is 4/3 now, JG, 4/3, GJ, damn it, 4/3. And our MJ, this is 3/2, so times 3/2. So the 3's cancel out, and we are left with 2 Bohr magneton times B. Now let's go for the next one. So here, the 6th one, this is going to be Bohr magneton times 4/3, and this time MJ is 1/2. So in this case, we get 2/3. And now we get the same thing, but with a minus sign, right? Because this time we have the same J, we have the same L, so GJ will be the same, the landé factor, but the M will be different. So here we will have minus 2/3 Bohr magneton B. And finally, we have, let's take blue again. So E8, because of the Zeeman effect, will be the same as the first, but with a minus sign. So minus 2 mu B. All right, so these are the energy corrections to the energy levels because of Zeeman effect. But you have to consider that this isn't the entire thing, right? This is only the corrections. This goes on top of what we already had. So let's go and check that out. So basically, what I mean, maybe let's go for a different page before I do that, is that basically our total energy is of course going to be the energy of the hydrogen atom, like the one that we saw before without any corrections, plus the one with the fine structure, plus the correction from the Zeeman effect. All right, so we need to go back and see what our results was for this part. Now this energy is what I wrote down in this formula right here. This is something we have already shown. This part is the normal energy levels for the hydrogen atom without any corrections, and this part is the relativistic correction plus the spin orbit coupling. All right, so this is basically everything except for the Zeeman. So yeah, let's go for our case. So if we have n equal 2, this will be rewritten a little bit. So this will be e to j, and this will be minus 13,6 divided by 4. So minus, well, I already had a minus, whoops. So this is 13.6 electron volts divided by 4 times 1 plus alpha squared divided by 4, and then 2 divided by j plus 1/2 minus 3 over 4. So we have two possible values for j. We have j equals 1/2 and 3/2. So let's go for 1/2 first. So when j is 1/2, we get the same thing. So minus 13.6 electron volts divided by 4 times 1 plus alpha squared divided by 4. And then we get times, this is now 2 divided by 1/2 plus 1/2, which is 1. So we get 2 minus 3 over 4. But we can write this as 8 over 4, right? 2 is simply 8 over 4. So now this entire thing will be 5 over 4. So this entire thing will be 5 over 4. And well, we can now multiply it through, of course. And we will get 5 alpha squared divided by 16. So this is the energy of the hydrogen atom, including the fine structure, all right? And we will now do the same for j equals 3/2. So 2, 3/2. We will have the same minus 13.6 electron volts over 4, 1 plus alpha squared over 4. And this time, when we get 3/2, we will get down here at 2. So we get 2 divided by 2, which is 1, minus 3 over 4. And this thing is simply 1 over 4. So we get 1 over 4 times alpha squared over 4, which is going to be alpha squared over 16. So these are our two possible energy levels to which the Zeeman effect will be added onto. All right, so basically the end result energy for each level will be the energy that we found here, and then we have to add the corresponding energies. But don't worry, we're going to do that right now. Okay, so let's find each one of these states. Let's go back to our formula. So what we had is basically the fine structure plus this basic energy, which we already saw, which we called En. And to this, we want to add the energy from the Zeeman effect. So we have to keep in mind that there are only two possibilities for this base energy, and it depends on J. So for all the stage which has J equal 1/2, it's going to be this part. And for all the others, it's going to be this. So let's not worry too much. And I'm going to write it like this. I'm going to be a little bit lazy. So I'm going to have E1, E2, E3, E4. This is equal, this is equal, this is equal, this is equal. And here I'm just going to be like super lazy. 13.6 divided by 4 times 1 plus 5 alpha squared over 16. And then we're going to add each one of them. So then we have, what is the energy of the first one? the energy of the first state is the Bohr magneton times B. So it's going to be plus mu B times B. Then the energy of the second state, where was it? It was this. Yeah, it was this. So the energy of the second state is minus mu B times B. So basically the same thing, but with a minus sign. So minus mu B, B. The third state is 1/3. So plus 1/3. And then we get minus 1/3. So let's do the same, but with the other 4 energies. So now let's do the same for E5, E6, E7, and E8. So in this case, our energy will be 13.6. Oh, this is electron volts, by the way. Just as a reminder, so this is in electron volts divided by 4, 1 plus alpha squared divided by 16. And now we have to add each one of the energies. So for the fifth one, we had 2 Bohr magneton times B. Well, I'm going in the wrong direction. So we had 2/3 of the Bohr magneton times B. And then, oh, sorry, only 2. The 2/3 comes afterwards. So this is only 2. 2/3 comes now. So plus this, then we get plus 2/3 this, and I think that now comes minus 2/3. Yes, so now comes minus 2/3, and then we get minus 2. So these are our energy levels. So let's now make a diagram. So what would our diagram be? So we have our energy levels, and they depend on what do they depend? Just let me make sure that we are clear on this. So they depend only on the magnetic field strength, right? Everything else here is a constant. Alpha is a constant, the Bohr magneton is a constant, and these are just numbers. So let's do it like this. So we have our graph, and this is going to be our energy levels, and it will depend on the strength of the magnetic field, so B external. So what are our energy levels? So we have these values. Oh, what happened to the minus signs? Whoa, what happened to the minus signs? Did I include them before? Yeah, okay. Yeah, important correction, we need to include the minus signs, of course. All right, so what are our energies? They are, where are they? Here. So we have this base energy, and to that we have to add or subtract the corresponding energies. All right, and the same thing here. So which one of these is larger? So they are both negative numbers, but this one has 5 times alpha, so this one is going to be larger. And since they are negative, that means that this is simply deeper down. So that is this part right here. So this is minus 13.6 over 4 times 1 plus alpha squared times 5 over 16. And from this, we have 4 distinct energy levels. 1, 2, 3, 4. And they are, I'm already lost again here. So they are plus, let's see, which ones are the largest ones? So this one is the biggest, then comes this, then comes this, and then comes this, right? Because we are making it bigger, bigger, smaller, and even smaller. All right, so we get, this is maybe a different color, so this is mu0b, this is mu0b over 3 minus mu0b over 3, right? We raised the energies here, and now we are lowering them, and this is minus mu0b. So what used to be a single energy level has now become 4 distinct energy levels. So we have broken the degeneracy of this level. This is why we call this the Zeeman splitting, all right? And The other energy level is right here. Maybe I'll change the color. This is minus 13.6 over 4 times 1 plus alpha squared over 16. Of course, this is not necessarily to scale, all right? Keep that in mind. And we have 1 energy level, 2 energy levels, 3 energy levels, and this is going to be a bit tough in terms of space. And what are the levels themselves? That's 2. Let's see, which one are the biggest? So, oh, this one is actually in order. That's nice. So it's going to be 2. Oh, wait, why is this? When did this become mu0? Mu b, mu b, mu b, mu b. Sorry, Bohr magneton, of course. And this is 2/3 Bohr magneton times b minus 2/3 Bohr magneton times b. And this right here is minus 2 Bohr magneton times b. All right, it got a little bit messy. And what are the slopes? Well, since our variable here is b, you can think of this as being y equals mx, right? Where x would be b in this case, and m would be whatever is accompanying it. So in this case, our slope would be 2 times the Bohr magneton. Here it is 2/3 times the Bohr magneton, and so on. So here we have found everything we needed. We have the energy levels, we have the slopes, we have made the graph, and this is the weak field Zeeman effect. So we see that we now have these splittings. However, they do not happen at equal intervals. That's kind of why this is called the anomalous Zeeman effect. So these splittings are not like symmetrically done or separated, which does happen in the normal Zeeman effect. So I hope that this was useful to you. I'll see you in the next video. Thank you very much for watching.